All right, here's another problem to review the idea of maximizing utility, income, and substitution effects with a bonus idea involving subsidies and why they are bad. There are a lot of countries in the Middle East and other places around the world that try to help their citizens by subsidizing something. It means artificially lowering the price of something, and the government has to spend tax dollars on these things. And what it does is it causes people to overconsume the thing that's being subsidized, and I guess it makes people better off in a way until you remember that whenever the government spends money, they have to get that money from somewhere. They have to tax it from people. So really what you're doing is you're reducing people's income in order to subsidize this thing. So what we're going to do in this problem is we're going to do a standard analysis of maximizing utility. We're going to see a change in a price, maximize utility again. Then we're going to do the hypothetical decomposition basket here, and we're going to break apart the substitution and income effects. And then we're going to imagine that this first situation, we're talking about here two goods, gasoline and Y. Let's think about Y as being all other goods that you might spend your money on. So our utility function here, U equals gas to the 0.2 times all other goods raised to the 0.6 power. So we're going to imagine that this 60 cents is actually a subsidy, and that's money that is either coming out of people's incomes, or it's money that the government could give people in cash, and see which would make people better off, the subsidy, or just either reducing their taxes or increasing their income in some other way. So let's dive in. So we're going to give this person a budget of $100. And the price of gas is 60 cents initially. Price of all other goods is $1 per unit of all other goods. Maximize their utility. Well, using our marginal rate of substitution shortcut rule. The marginal rate of substitution for this utility function is going to be 0.2y over 0.6x, or g in this case. Let's just call it x, so that if you're used to using x and y's, it's not going to mess you up. But here we're thinking about x as being gasoline that is being subsidized by the government. Set that equal to the ratio of the price of x, 0.6, divided by the price of y, 1. Right? So we don't really have to divide it by 1. Let's just simplify it to be the 0.6. Dividing by 1 doesn't do anything. So that's our first equation. Second equation is just the budget line. 0.6x plus 1y equals $100. So let's solve this first equation, substitute it into the second equation. Let's solve this first equation for y. So multiply both sides by 0.6, we get 0.2y equals 0.6 times 0.6 is 0.36 x. Divide both sides by 0.2 and I get 1.8. So we get y equals 1.8 x. I'm going to use that equation twice. First, we're going to use it to plug it into this equation here for y. So that's pretty simple in this case. So we get 0.6x plus y. Well, y is 1.8x equals 100. So we get 1.8 plus 0.6 gives us 2.4. X equals 100. Divide both sides by 2.4 and we get 41.66666. Let's write it over here. X equals 41.66666. We can round it off to 0.67 at some point. And y equals, here's the second time we use this equation. Y is 1.8 times how many x's we use. So that's going to give us 75. The last thing we want to do in this standard kind of problem is figure out, well, how much utility is that going to give this person? Plug our optimal values, sometimes people will call these x star and y star, plug those optimal values into the utility function up here and see how much utility you get. And I get about 28.12. So in this situation, we would predict that this person would buy 41.6 gallons of gasoline and $75 worth of all other goods. Okay, now something changes. So now the price of gas, imagine in this situation, the government was subsidizing the price of gasoline, and now they say, we're not going to do that anymore. We're going to let the price rise to its natural price in this market, and that is $1 per gallon. Now what is this consumer going to do? Well, obviously they're going to be angry because their utility is going to go down, but let's see by how much. Okay, so our first equation, the same marginal rate of substitution, 0.2y over 0.6x equals the ratio of the prices is now 1 over 1, or just 1. Second equation, budget line. Now it's 1x plus 1y, because the prices are 1 each, equals 100. So, solve the first equation for y, 0.2y equals 0.6x. That's going to be y equals 3x. So, again, just like last time, we're going to use that equation 2 times. First time, we're going to use it to substitute y equals 3x in this budget equation over here. So we have x plus y equals 3x equals 100. 4x equals 100. So x is going to be 25. So when the price goes up, people are only going to buy 25 units of x. Let's see what happens to how much y they're going to buy. Well, we see from this equation that y equals 3 times the amount of x. Y is going to equal 75. And again, this is a common side effect of using a Cobb-Douglas utility function. When you raise the price of x, the amount of y doesn't change. So x star now 25, y star, optimal amount of y 75. Let's see how much utility that's going to give us. Plug it back into that utility function. So now x is 25, so 25 raised to the 0.2 power times 75 raised to the 0.6 power, and this person is less happy. 25.39 is their utility. So when countries do this, of course, their people are unhappy. So what could we do about that? Well, we'll talk about that in a minute. First, let's do the standard thing that you want to do with utility maximization problems when a price changes, and let's talk about income and substitution effects. So let's determine this hypothetical decomposition basket that is going to give us an intermediate solution in between 41.67x and 25x, and it's going to let us break apart how much of the difference between 25 and 47 is due to income effect, people feeling poorer, and how much of it is due to the substitution effect. People are buying less gas because now it's relatively more expensive than it was compared to all other goods. So for the decomposition basket, this hypothetical thing, we set up 2 equations. First equation, same as before. So basically we're pulling this part out of the second part, because what we want to do is use the same marginal rate of substitution as always. 0.2y over 0.6x. And we set that equal to the ratio of the new prices. So this decomposition basket, we're thinking about new prices, what's going on. But what we want to do is get people to the old utility. So that's the first equation. Marginal rate of substitution, ratio of the new prices. Same thing we had here. Second equation, it can't be the budget line because we don't know the budget. That's one thing we want to know out of solving this problem. So the second part of the second equation here is going to be this. What was that old utility level? Well, the old utility level is 28.12. And that's equal to the utility function, x to the 0.2 times y to the 0.6. So the second equation gets them back to that old utility level. And we want to know what's the cheapest way to do it. So our procedure, solve this first equation for y. Oh, we already did that before, right? Right here. Y equals 3x. So we can recycle that part of the problem as well. And now we want to plug that in here for x. Sorry, not for x, for y. Y equals 3x. So we plug in 3x here for y. And remember when you plug in that 3x for y, that the 3x, the whole thing has to be raised to the 0.6 power. 28.12 equals x to the 0.2 times 3x, all to the 0.6. Now the easiest thing to do, since both the 3 and the x are multiplied times each other, you can distribute that exponent, that 0.6, to the 3 and to the x. And then we simplify and group everything. So we're going to have 28.12. We're going to want to divide both sides by that 3 to the 0.6. And 3 to the 0.6 is 1.93. So let's put that on the bottom, 1.93. And that gets rid of the 3 to the 0.6 here on the right side. And then we want to group those x's. We have x to the 0.2, we have x to the 0.6, that's x to the 0.8. So what is this 28.12 divided by 1.93? That gives us about 14.57. 14.57 equals x to the 0.8. And now to get rid of that 0.8 power, we want to raise both sides to the 1 over 0.8 power. 1 over 0.8, 1 over 0.8. That leaves us x on the right-hand side, and whatever 14.57 raised to the 1 divided by 0.8 power gives us. I get 28.47, roughly. So our answer, optimal amount of x, 28.47. How much y is the person going to buy? Well, again, this equation over here tells us y is 3 times that. So times 3 gives us about 85.4-ish. So this person would spend $28, since gallons of gas are $1 a piece, right? So they'd buy 28.47 units of X, 85.4 units of Y. Again, they're $1 a piece. And what we want to know is how much money is that going to cost? And in this example, this is pretty simple. We just want to plug it back into a budget line, assuming that each of these goods is $1. This budget line right here. Except we don't know what the budget is in this case, right? So we just want to see what x plus y is. 1x plus 1y. So we just need to add up the 85.4 plus 28.47. It's going to cost $113.87. And that is the cost to get this person back to their old utility level of 28.12 at the new prices, which are $1 each. Okay? So now let's figure out substitution and income effects. And I always find a little visual way is the best way to start, and then break them apart. And we'll graph all of this in a minute. All right, so let's put the low value of x in this situation on the left. So the lowest was this 25. So let's write that on this left side. So, and the high value for x we had was this 41.67. That was before the price went up. And then we have this intermediate hypothetical solution in the middle. Now, again, it's not going to be exactly in the middle. We want to visualize this properly. So this is 28.47. Well, that's a lot closer to 25. So it's going to be somewhere over here if we were to do this correctly on a number line. So let's graph this, because rather than memorizing which of these differences is the income and which of these is the substitution effect, let's graph them and think about it that way. Let's go to our indifference curve map here, and let's graph these 3 situations. Situation 1, we had $100, so let's call that situation A. The budget was $100, price of X was 60 cents, and the price of Y was $1. So with $100, we could afford 100 Ys with that. With $100, 100 divided by 60 cents each, we could afford 166.6666 X's. All right, so it's going to put us about there. Connect those 2 dots, we have a budget line. So there we go. And what we're looking for is this indifference curve here for about 28 utils. That's what we were getting in this first situation. So that's this blue one. We should be tangent. The slope of the budget line should be equal to the slope of the indifference curve at that point. And our solution was X is about 42 and Y is about 75. So we'll go over here to about 42, here to about 75, and that ought to tell us that point right there is our optimum solution. The graph checks out. We're spending all our money, not too much, not too little, and the slopes look like they're equal at that point. And the indifference curve we're tangent to is the right amount of utility. It's about 28. All right, in our second situation, we had, call that situation B, we had $100, but the price of gas was 1, price of all other goods was also 1. draw our new budget line. Well, we can still afford 100 Ys. Now we can only afford 100 X's. $100 divided by $1 a piece. So let's draw that budget line. And what we're looking for here is that we should be getting about 25 or so utils. That's what our answer said up here, right? 25.39. So we're getting a little bit more than 25 utils, which means we ought to be able to be getting a little bit beyond this indifference curve here for 25 utils, and we can. You can see a little bit of gap right there. And our solution was, the solution for problem 2 was 25 X's and 75 Y's. Our optimum point was about here, 25 and 75 for point B. Checks out. All right, so now our decomposition basket. Let's see, we had $113.87. And the prices were $1 and $1. Let's draw our budget line here. About 114, okay, just here a little less than 115. And then down here, about the same. Slope should be -1. About 29 and about 84 is going to put us about here. Let me use red so we can identify that point a little better, and that's our point C, our decomposition basket. And as you see, C is between A, the before, and B, the after, and that is going to decompose it into 2. Now, which of these 2 differences, which of these changes is the income effect and which is the substitution effect? When you look at between A and C, what we're doing is we're rotating the budget line around the same utility. So that's not the income effect because we don't feel worse off, we don't feel poorer. All we're doing is changing the ratio of the prices to isolate the substitution effect. Between C and B, however, you see what we're doing is we're sliding this red budget line back to B, which means it's a parallel shift. We're changing the income. So between C and B, that is the income effect. So when we go back to our little graph, breaking it down here, we see this is the original point, A. The middle point is C. This last point is B. Between A and C is the substitution effect. So we can see the substitution effect is much, much, much larger here than the income effect, which is the much smaller difference here between 28.47 and 25. So to explain this in words, the total difference between 41.67 and 25 is 16.67. And out of that total decrease in purchases of gasoline of 16.67, we can say that 3.47 of it, the difference between 25 and 28.47, is the income effect, and the remainder, 13.2, is the substitution effect, the effect that comes from the change in the opportunity cost, or the relative price of the 2 goods. Question number 5 here says, what's the compensating variation? Explain what it means. Well, the compensating variation is just how much money do we need to give you to get you back to the old utility at the new prices. And in this case, that's $13.87, because that's the budget. The budget you'd need is $13.87 more. And make sure you can explain that. So what is the compensating variation? $13.87. What does it mean? That is how much more money we would have to give this person to compensate them for the increase in the gas price. To keep them at the same happiness level they were before. One last point. Since in this context, what I was talking about was assume there's a government subsidizing gasoline at 60 cents. That means they're paying 40 cents in the beginning, right? So they're paying 40 cents for each gallon that people buy, and that money's coming from somewhere. How much is that subsidy costing them? And basically what they're doing is they're spending money in the first case to get people to this utility level of 28.12. How much is that costing them? Well, if people are buying 41.67 units. 41.67 times the 40 cents means that for each consumer, they're spending $16.67, roughly. That's the cost of the subsidy. So when many nations get rid of these subsidies, people are really mad. Okay, well, how about you go and do something nice for your people? You don't want to spend the money on this wasteful subsidy. How about you go do something nice for your people? Send them a check or do something nice for them. How big would the check have to be that you send people to make them just as happy as they were before the subsidy? $13.87. That would be a whole lot more efficient way to get people back to their old utility level at the new prices after you remove the subsidy. So this is a demonstration of how you can save money by getting rid of subsidies, and you can spend less money on some other kind of way of making people happy, and it's just a more efficient way of doing things. All right, let me know if you have any questions about this. Talk to you later. Bye-bye.